Welcome to a lesson with Dr. Powell. Let's look at an example of an additive group and talk about what it is. A group is simply a set with an operation. This operation needs to be well defined. We can call that closed on the set. So if you add two things, this is an addition table. If you add two things, 2 and 3, and see what it is, and 3 and 3, and so forth, you can add any two things here and you get something else in the set. So we have a well-defined addition operation, or it's closed under addition here. Now, we also need to check that there's an identity. That's something such that when you add by it, you get the same thing back. So for instance, you have 0 plus 1 is 1, 0 plus 2 is 2, 0 plus 3 is 3, and so forth. Notice it does nothing to what we are adding by. It just produces the same thing back. So adding by 0, so that means 0 in this case is representative of an identity with this addition table. That's nice. So we have a well-defined addition. It has an identity. We also need inverses. That means every element should have an inverse, meaning another thing to add by such that you get the identity. 3 plus 2 is 0. 2 plus 3, okay, 0 there. 1 plus 4 is 0, and so forth. Notice we have a 0 in every single column or every row, since we have inverses. Now, it's true that if you have inverses, you can actually show that it will be the unique inverse. Okay, but we'll keep going here. So we've checked that it's closed. We have an identity, which is 0. We have inverses. All right. The last thing we need to check to see if it's a group is associativity. Now, notice a couple things here. So what is associativity? Associativity is this idea: A plus B plus C is equal to A plus B plus C. In other words, we can regroup. Naturally, when you add in the integers, Z, addition is associative. Now, really what's happening here, see from this 0, 1, 2, 3, 4, and what we're adding here, notice how you have like shifts of things over. Like this line is a shift of that line, is a shift of that line, is a shift of that line, and so forth. Actually kind of what's going on, if you think of these numbers as simply representing ideas, such as this 0 representing something like multiples of 5, this one being like 1 more than a multiple of 5, 2 more than a multiple of 5, 3 more than a multiple of 5, 4 than a multiple of 5, then actually this table actually gives you the rule for what happens when you add a number that's 2 more than a multiple of 5 to one that's 3 more than a multiple of 5. You end up getting a multiple of 5. That's what this says. So if you interpret it that way, you realize that the addition here is actually inherited from Z, where associativity already lives. So it actually inherits associativity. In general, in the linear algebra book where this is coming from, or in the class where this is being taught, associativity will be often taken for granted. Sometimes we'll show it, but often we'll just, we won't really check it, but just realize that it is inherited from another location. There's other ways of checking associativity here by actually thinking of the lines that are here to here as actually compositions of, you can actually think of what's happening here with this operation as composition of functions from line to line, and composition is associative, and you get associativity that way. There's a few different ways of doing it, but in any case, we're going to think of it as being an inherited property. It's a little harder to check. But nonetheless, we have closure, identity, inverses, and associativity. All these things holding make a group a group. So the real numbers with the operation of addition, that's a group. The integers with the operation of addition, that's a group. We have lots of different groups, but we all can also have finite groups. And this is an example of a finite set that has a nice, well-defined group operation where all these conditions hold. Thanks for watching.